Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting compound is malic acid or fumaric acid, butanoic acid, represented as CH2H vertical bar CH2H, meaning both carbons of a double bond each bear a CH group. This is specifically the structure of an alkene diacid, malic fumaric acid. Moving on to the next step. 2 moles of NaOH neutralize both carboxylic acid groups to give the disodium salt NaOCH is equal to CH2Na. This is compound A, the disodium salt of the diacid. Moving on to the next step. In Kolbe's electrolysis, carboxylate anions are oxidized at the anode, losing CO2 and generating carbon radicals, which then couple. For the disodium salt of an alkene diacid, NaOCH is equal to CH2Na. Electrolysis at the anode causes each CH group to lose an electron and release CO2. This leaves radical centers on the 2 carbons, CH is equal to CH. These 2 radical centers are already bonded to each other, intramolecular, so after loss of both CO2 molecules, the result is a diradical that forms a triple bond, HCCH, acetylene-ethine. And for the final step, A, CH3-CH3, this would result from Kolbe electrolysis of sodium acetate, CH3CONA, not from a diacid with a double bond. B, H to C is equal to CH2, this would result from Kolbe electrolysis of sodium succinate, NaOC, CH2-CH2CONA, where after loss of 2 CO2, 2 CH2 radicals couple to give ethylene, but that requires a single bond between the 2 carbons in the starting salt. D, CH2 is equal to CH is equal to CH2, 1, 3 butadiene. This would result from intermolecular coupling of 2 vinyl radicals, not the intramolecular product expected here. C, HCCH, correct. The disodium salt of malic fumaric acid, with CH is equal to CH backbone, upon Kolbe electrolysis loses to CO2, and the 2 remaining carbon centers, already double bonded, form a triple bond giving acetylene. Therefore, the correct answer is C. Therefore, the correct answer is option C.